Hi, my name is Shelby Taylor. I am from Morro Bay, California, and I am part of Working Group 1. Our team name is S.H.I.E.L.D, which stands for Soil and Hydrology Intelligence for Emerging Land Cover Disruptions. Our project is about predictive modeling of flash floods, investigating hydrology and land cover dynamics through remote sensing data. To come up with this project, we actually combined two of our proposals, one on soil properties and one on flood risk. This project is important to us because flash floods pose significant risk to infrastructure and human safety. In Texas and New Jersey, ongoing floods have caused an unprecedented loss of life and damage to affected communities. Monitoring topographic, hydrologic, and soil data to understand repetitive trends during flood events can help to minimize damage in the future. Our method to do this, we will analyze areas of interest focusing on hydrology, topography/elevation, runoff, land cover, soil properties, and other factors that could lead to flash floods and river overflows. Some of the data we've used includes the land cover observations we compiled through the Globe Observer and EarthMap.
Hi, my name is Khushi Patel. Growing up in Sugar Land, Texas, I've seen firsthand the impacts of flooding events, particularly during hurricanes such as Hurricane Harvey and Hurricane Beryl. Deciding to investigate what particularly causes an area to be flood prone, I chose to first take a look at this 3 kilometer grid pasted to the left. Below that, I've analyzed the same grid but using different layers on EarthMap Online. Firstly, at the very far left, I've analyzed surface water runoff. Next is different soil types. Next to that is surface water occurrence, with bright reds representing an increase. And lastly, the slope of the area I live in, with paler colors representing a more steep slope. My team and I hope that analyzing these factors can help us gain a better understanding of what causes an area to flood more easily, or what mitigation efforts we can take to prevent an area from experiencing as much damage as it may from a flood event. Thank you.
Hi, I'm Bhattacharjee. I live in Edison, a town located in central Jersey, which has seen numerous flooding events in recent years. My region is flood prone, and recently we have experienced multiple extreme weather events involving flash flooding and storms. In an effort to figure out what makes my region so flood prone, I started by analyzing my AOI, or area of interest, using various layers from EarthMap Online. In the bottom right corner, you can see my 3 by 3 kilometer AOI in EarthMap Online without any layers applied. On the far left, the first layer I chose to analyze was the layer for yearly runoff. Runoff is usually highly correlated with flood risk, with flash floods being major sources of high runoff. However, the light purple and white coloring represented relatively low levels of runoff. Runoff alone cannot explain the flood risk in my area. Next, I analyzed soil types, theorizing that maybe the soil types in my area had higher clay content, leading to slow drainage of water from high rainfall events. But soil type didn't quite explain it either. The dominant soil type in my AOI was loam, which is a relatively balanced soil with minimal drainage issues. In this slide, we can see some pictures of the recent flooding in my area, which gave me a hint as to why this was happening. If you look closely, you can see that in both pictures, the flooding is concentrated around roads, in other words, impervious, non-porous surfaces, which would prevent natural draining by blocking water from seeping through. This led me to analyze the history of urbanization in my AOI. In this slide, you can see a graph of land use categories over time in my AOI, with red representing urban development and green representing natural forests. The graph shows a clear trend from 1995 to 2020 of increasing urbanization and decreasing natural coverage, leading to a loss of drainage opportunities and increasing flood risk over time. Finally, the last piece of the puzzle lies in analyzing precipitation patterns. In this graph of monthly aggregate precipitation from 1981 to the present, I found high seasonal variability in monthly precipitation. Although yearly precipitation is not particularly high in my AOI centered in North Edison, monthly aggregates get as high as 150 to 200 millimeters per month almost every year in late summer due to hurricane season, leading to a consistent summer flooding risk in coastal regions or regions of New Jersey near rivers, like mine. This investigation into my AOI really emphasized the importance of considering every variable in a situation as complex as flood risk, an ideal which our S.H.I.E.L.D project adheres to.
Hey everyone, my name is Aryan Venishetty and I'm from Monroe, New Jersey. In recent years, NJ has experienced increasing rainfall and precipitation, leading to constant flash flood warnings and accidents on our highways. Branching off our experience analyzing land cover in our Dr. Pixel project, I analyzed my same AOIs using different EarthMap datasets related to precipitation, runoff, as well as the land elevation and slopes. On the top row, you can see my AOI's data for precipitation, but it's worth noting the lack of variability because in the grand scheme of things, a 3 kilometer by 3 kilometer area is not very large. But next to that, you can also see the historical data from millimeters of rainfall, both monthly averages over the years, as well as average rainfall since the 1980s. You can see that the average rainfall peaks in the summer months, July being over 110 millimeters. And in the bottom left, I've included snapshots of surface water changes, red representing an increase. To the right of that is my AOI's elevation and slopes visualized, the different colors representing different slopes and valleys. Our team, S.H.I.E.L.D, hopes Earth maps visualization and data can help us answer what makes an area flood prone and what we can do to make these areas better prepared for disasters.
Hi, I'm Kumudha Srinivas, and the area of interest for my case study was Dublin, California. Dublin is a rapidly growing city in the East Bay area with minimal flood risk and a very limited history of flooding. Using the hydrology layer on Earth maps, I found that there was approximately 100 millimeters of runoff per year in Dublin, which is on the lower end of the spectrum. The soil texture filter revealed something very interesting. Although Dublin isn't a flood prone region, it has a large amount of clay loam soil, which typically implies higher runoff amounts and consequently a higher flood risk. This stood out as a discrepancy until I examined the city's precipitation levels. The linear fit of the annual aggregation chart showed a decreasing trend, and the highest amount of monthly average rainfall was only about 87 millimeters. Therefore, the minimal rainfall accounts for the reduced runoff, despite the soil type discrepancy. Discovering such patterns and trends in hydrology, land cover, and topography is essential to predicting flood risk and alleviating future destruction.
Hi, I'm Satvik from Suwannee, Georgia, a region not typically prone to flooding. To understand why, I analyzed local hydrology, soil texture, and precipitation. Using EarthMap datasets, I found out that Suwannee experiences peak surface runoff from January to March, with a maximum of 28.42 millimeters in February, but the overall runoff remains moderate, which is around 290 millimeters per year. Soil data revealed a transition from loam at the surface to clay loam at deeper depths, which slows water infiltration. This layered soil profile, combined with moderate rainfall and higher elevation, reduces flood risk despite occasionally high runoff. Additionally, Suwannee has a minor risk of flooding over the next 30 years, according to the 2024 Suwannee, Georgia Flood Map and Climate Risk Report. ERA5 land precipitation confirms this, showing that rainfall peaks in winter months like January and March, while drier months in the fall help balance the wet season. Together, these factors support long-term climate resilience and effective flood mitigation.
Hi, I'm Pallavi Nair from Allen, Texas, a region notably unaffected by floods or flash floods. To understand why, I analyzed hydrology, soil texture, and slope. Firstly, the runoff is very minimal, with a majority facing around 100 millimeters of runoff. Interestingly, the dominant soil types, clay and silty clay, have high water retention, which would usually increase flood risk. So, while soil texture raises questions, the minimal runoff combats this anomaly. Additionally, the slope map shows that most of Allen has a flat to gently sloped terrain, which helps reduce rapid water flow and pooling. Additionally, recent climate reports confirm that Allen faces only a minor flood risk over the next 30 years across residential, commercial, and infrastructure sectors. Together, these factors suggest that Allen's topography plays a critical role in mitigating long term flood vulnerability.
Here is a table from my poster that combines my own ground observations with remote sensing data and image chips. Each row represents data from one of 37 points in our 3-kilometer area of interest grid. Comparing our own globe observer pictures with different remote sensing layers and graphs allows us to discover patterns, trends, and inconsistencies within our areas of interest.
Hi, my name is Saad and I'm from Tyler, Texas. One key focus of our project has been the integration of AI and machine learning and enhancing flash flood prediction using remote sensing data. We specifically plan to model the key hydrologic processes of rainfall to runoff transformation, rapid floodplain inundation, and flood routing to assess factors that contribute to flash flooding. To do this, we're processing satellite-derived inputs like Sentinel land cover, daymet precipitation, and SMAP soil data within Quantum GIS software to delineate catchments, extract hydrologic and topographic features, and analyze land cover dynamics. We're also working with HEC-RAWs, where hydraulic simulations can help us map inundation extents, giving us insight into the potential risks of flooding caused by land cover, weather patterns, and soil properties. These models will be validated against discharge hydrographs and ground observations. By fusing physical modeling with machine learning, we aim to develop a hybrid predictive system that can adapt to changing land cover and climate trends, improving both lead time and spatial accuracy of flood forecasts. Our end goal is to deliver a scalable, AI enhanced flood risk platform to support operational decision making in emergency response and long term hydrologic planning. This approach enables more effective, data driven flood risk management, especially in areas with limited ground observations or rapidly changing land use. Thank you.
Hello, my name is Hector Galvan, and this is our project timeline. Basically, just a sequence of steps we're going to follow in the months leading up to AGU and the annual meeting. So our first step, which is already mostly accomplished, was gathering data for our own AOIs, or areas of interest, relating to our project theme, such as soil properties, elevation, runoff, among others. Our second step will be to expand our AOIs to other areas that have recently suffered flood events and are more flood prone, such as Kerrville, Texas, and Plainfield, New Jersey. Our step number 3 is artificial intelligence. Here, the team plans to develop an AI that can predict high-risk flood zones by using our past data collection and meteorological forecasts. For our step 4, a web-based platform, we want to develop a website in the format of an interactive map to showcase our AI's predictions and send notifications or warnings of possible flood events. We also want to allow for citizen science entries, including pictures and soil samplings, which could allow us to ground truth and validate the data that we're using to train our AI. In the future, we want to make this website public so that everyone can benefit from the project. Finally, our fifth step, though still in the brainstorming process, we do want to have a physical component to this project, and ideally we want it to be easily deployable, potentially be used by citizen scientists, and of course provide the invaluable ground truth data that we need to train our AI and to validate the data sets that we're using.
Hi, I'm Arush Choudhury. One of our biggest challenges during our data collection process was technical, losing data and images on the Globe Observer app, and it forced us to redo fieldwork or work with incomplete data, slowing down our progress. Socially, one of our biggest challenges was dealing with awkward moments and having to explain to homeowners why we were standing in places such as the middle of the road and having to take directional pictures that included their and their neighbors' properties. Through all of this, we learned valuable group skills like teamwork and communication, especially working across different time zones, schedules, and commitments as a group of students across the country. And we also learned other skills such as problem solving and other technical skills. Here are some personal reflections from our team members. Here is a representation of our brainstorming process, timeline, methodology, and future plans, all put together. Thank you to our mentors, Dr. Rusty Lowe, for your guidance and support throughout this program, Dr. Peder Nelson, for always being enthusiastic about our questions, Cassie, for always making sure that we submit our forms on time, Dr. Andrew Clark and Dr. Erika Podest, for your insightful feedback during our meetings, and our peer mentor, James Ervin, for sharing his valuable SEAS experience throughout our research project. On behalf of the whole team, we'd also like to thank the C staff, Selena Miller and Margaret Baggio, for organizing this incredible program. Lastly, thank you to all our partners at UT Austin's Center for Space Research, NASA, and the Earth Science Education Collaborative for making this opportunity possible.